Hello! In this video we are going to see another example of function, mathematical function that is applied in the real life. In this case it's going to be called elliptical speed of an object orbiting a main body. Okay, which are the objectives of this video? We are going to explore several types of orbits, including the elliptical orbits and new orbits called Molniya orbits. And we also will apply mathematical functions to calculate the orbital speed. Requirements, as usual, not so much. Some calculus, when we need to calculate some derivatives, and some ability to interpret mathematical models. But I think you won't find this video difficult. Okay, so elliptical orbit. What is an elliptical orbit? It's when we are orbiting around a main body, but the orbit is not circular. It has the shape of an ellipse. In order to calculate things, in order to see these things better, we need to define two main ideas. Remember that in an ellipse we have the major semi-axis, that is the distance between the center to one side of the ellipse, the longest side. But we are going to define the periapsis and the apoapsis. The periapsis is the point in the orbit closest to the focus. Be careful, not the center. An ellipse has two focus, the main focus and the secondary focus. Okay, the main one is very close to one side of the ellipse. This is the periapsis, and the farthest point is the apoapsis. Okay, in this case we need this information, but we are going to deal with semi-axis first. I mean, by the way, an important property about ellipses: the radius of the periapsis plus the radius of the apoapsis is 2 times the major semi-axis. This is a very important formula and makes sense if you just plotted the ellipse. We will see examples about this, don't worry. Okay, but how do we calculate the speed of an object orbiting in an ellipse, or in an elliptical orbit, sorry? The function is very similar to the circular speed, but it's obtained in the following sense. The speed depends on the distance from the center of the main body, the main focus. In this case, let's suppose it's the Earth. R is the distance that, from the center. A is the major semi-axis of the ellipse. Okay? And for sure, mu is the standard gravitational parameter of the central body, suppose that is Earth, and we have mentioned everything in the formula. Yes. Okay, so it's a very simple formula. It's very, very simple. It's only a square root, and inside we have 2 quotients, so it's not complicated. Okay, can we give an example of an elliptical orbit? Yes. For example, Molniya orbit. A Molniya is a highly elliptical orbit. An important fact of ellipses is the eccentricity. Very high eccentricity moves between 0 and 1. The highest eccentricity we have, the more flat is the ellipse. In this case, we have a highly elliptical orbit. It's very, very elliptical in this case. And the inclination with respect to the equator plane of the Earth is 63.4 degrees. That is not casual, okay? These degrees are set in order not to change the orbit during time, but we will see this in next videos. The orbital period is about 12 hours, okay? It takes 12 hours to rotate the Earth. Okay, why is this satellites or these orbits important? They are important if we consider communications, weather observations. Okay, the best way to observe the Earth and not to have a full visibility from the Earth is a geosynchronous orbit. That means I put a satellite in the equator rotating at the same speed the Earth rotates. So I have the satellite always pointing at me all the time. The satellite don't go up and down. It's just fixed in the sky because it's rotating at the same speed I'm rotating. Okay, but for higher latitudes, this is not so nice, okay? close to the equator is perfect. But if we are living just in the North Pole, we don't have high communication with the satellites, very complicated. In these cases, Russian people designed what is called the Molniya orbit. Molniya meaning lighting. In this case, we are going to see next, it's a highly elliptical orbit, as we mentioned before, that stays or remains very long time above the equator, and when it passes through the closest point to the Earth is going really fast. That is where the name lighting comes from. It's very fast, very close to the Earth. And the distances are very nice. Okay, the closest point is about 400 kilometers from the Earth's surface. The highest point is more or less like a geosynchronous orbit, 40,000 kilometers more or less, and we are going to see next. Okay, this is an example of a Molniya orbit obtained from SDK software. You can see this is the Earth, the equator plane is more or less like this, and as you can see, it's a very highly elliptical orbit. The satellite is now here, okay, it's orbiting, and one of the main facts that this orbit works is that the speed during the orbit is not constant. It's only constant when the orbit is circular. When it's not circular, the speed is different. This is also obtained by Kepler's law. The idea is the farther we are, the slower we move. And the closer we are to the Earth, the faster we move. Okay? So it's from this point to this point at the end, we have visibility from the Earth. When we don't have visibility, it's a very short time because it's going very fast in the periapsis here. Okay, this is a comparison between a Molniya orbit and a geosynchronous orbit. As I told you, this is a very nice orbit to have visibility from latitudes close to the equator. But for higher latitudes, the best way is to use a Molniya orbit like this. Okay, here I just add this visibility so you can see. Geosynchronous orbits, have the visibility from almost half of the Earth, okay? And Molniya orbits, when it's high enough, when it's moving farther from the Earth, visibility is always as good as geosynchronous for higher orbits, for higher latitudes, sorry. Okay, so you can see the visibility from this satellite. Okay, exercise. Can we calculate the speed of a Molniya orbit? At which point, you should ask, because speed is not constant. We are going to calculate the speed at the perigee and the apogee. The formula we are going to use, by the way, I didn't mention before, is called Biss-Viva equation. It's the function we used before. That one. Let me go back 1 second because it's important. This one. Okay? So, what do we need in order to calculate this exercise? We need the standard gravitational parameter of the Earth. It's given in kilometers cubed divided by second squared. This parenthesis is a mistake. R is the distance from the center of the Earth. The radius of the Earth is 6,371 kilometers. The altitude of the perigee, of the closest point to the Earth, is just 500 kilometers. And the altitude is 39,000 kilometers. So, as you can see, it passes through very close to the Earth and moves very far from the Earth in the apogee. And finally, given the perigee and the apogee, be careful, spoiler alert, we are using altitude and not radius. We need to add the radius of the Earth to these two values, The semi-major axis can be calculated as the radius of the apogee and the radius of the perigee. Then if you do that, if you calculate the semi-axis, you have R, it's R, by the way, the radius of the perigee is 500 plus the radius of the Earth. The radius of the apogee is 39,000 plus the radius of the Earth. Then you can see that the speed at the perigee is 10.03 kilometers per second, very fast. And the velocity or the speed at the apogee, the farthest point from the Earth, is 1.1 52 kilometers per second. So there's a very big difference in speed from the perigee till the apogee. Okay, so what have we seen today? We have seen basic principles of Kepler's law. In fact, we have mentioned two. One is the Bees-Viva equation, the other is the change of speed during an elliptical orbit. And we have seen an example of Molniya orbit. I hope you find this helpful for you. So thank you for your attention.